video begins, I'd like to make a few disclaimers. 1. This video will be factual and as unbiased as possible. If you were looking for some biased information, you would have gone to Fox News. 2. Portions of this video will go in depth with scientific explanations and details. If you're the type of person that cringes when you hear the word isotope, I've included small little links that will allow you to skip ahead. I don't recommend this, but sometimes it might go a little bit over people's heads or they just might not be interested in it. 3. Throughout this video, I'll use the phrases climate change and global warming, and I'll probably use them interchangeably, even though they are not the same thing. Climate change is just a broad term for a shift in Earth's climate, so it covers a lot. Global warming is specifically referring to an increase in global temperatures. When I say either of them, what I mean is an increase in temperatures caused by humans. The most important thing for anyone watching this video to understand is that the Earth is warming. That's why I put it first, why I put it before any other evidence. It's that the Earth's temperature has actually increased. Why has the Earth warmed so much recently? It's a great question, but in order to answer it effectively, we actually have to take a look at the past. Scientists can take ice cores out of places like Antarctica and Greenland, and when they drill them out, they can actually get to data that shows the temperature and also, interestingly enough, the composition of the gases in the atmosphere at that time. And looking back at the past 800,000 years, we can see that temperature and carbon dioxide are very closely correlated. A correlation does not always necessarily imply causation. So what I mean by that is that just because two things are related doesn't mean one actually causes the other. A great example, you notice that as it becomes brighter outside, you become hungrier. Well, that's not a causation, that's just a correlation, because as the day goes on, you get hungrier. The sun is not actually causing you to feel that way. In this case, however, evidence suggests that it is in fact a causal relationship. Carbon dioxide is very effective at trapping infrared wavelengths of light. And infrared wavelengths are the wavelengths that we associate with heat. So carbon dioxide actually traps those and forces them to stay on the Earth instead of radiating back out through the atmosphere. For those of you who are wondering why the changes in temperature happen at such regular intervals, it's due to the Milankovitch cycles. These are fluctuations in the way Earth orbits, and how its axis tilts, and where the axis is pointed. So first off, if you can imagine a spinning top, if you've ever seen it sort of go around in a little circle as it spins, Earth is doing that, but it's doing that really slowly. So where the axis of the spinning points changes. Another thing that changes is how steeply the Earth's axis tilts. Right now, it's about 23.4 degrees. But sometimes it's a little more, sometimes it's a little less. And that changes the intensity of the seasons on Earth, and therefore the climate. The third change that the Milankovitch cycles bring is how Earth orbits the Sun. It's a very minor change, but sometimes Earth's orbit becomes a little bit less circle-shaped and a little bit more oval-shaped. And this changes how much energy the Earth receives from the Sun. The point is, they are what instigate the change. Carbon dioxide doesn't instigate it, it just reinforces it and causes the massive changes, which are really only 5 to 9 degrees Fahrenheit, that are responsible for the differences between an ice age and a warm interglacial. How can scientists tell all of this fantastic data from just looking at ice cores? Well, there are two parts of the data that I mentioned: the composition of the atmosphere and temperature. I'm going to start with the easier one. The composition of the atmosphere is determined just by looking at what's inside little air bubbles that get trapped in the ice. You just measure that because it's a little snapshot of the atmosphere. Temperature is a little bit more interesting. Hydrogen has naturally occurring isotopes that have one neutron in them, and it takes more energy for these isotopes to be lifted into clouds by evaporation and then to be delivered as snow from the clouds. When temperatures are warmer, higher ratios of this isotope can evaporate into the atmosphere and form clouds and therefore form snow. So when scientists can measure this and get an accurate take on exactly how warm it is in the atmosphere. Humans emit a lot of carbon dioxide. To generate power, we emit about 1.6 billion metric tons of carbon dioxide. And just to get around, our transportation emits about 1.8 billion metric tons of carbon dioxide. And those two together account for about 61.8% of all carbon dioxide emissions in the United States. People might point out that it's not a significant figure. This couldn't possibly be impacting our atmosphere. Relative to other sources of natural emissions, like the ocean or forests where things decay, yes, it is tiny. But what you have to keep in mind is that the oceans and the forests also take this carbon back in. Humans, on the other hand, do nothing of the sort. Humans do not take carbon dioxide back out of the atmosphere. And that's why our impact is significant. If you seek out heat like you're cold-blooded, and I'm not going to mention any names, but Mom, then you might think, but warming temperatures would be great. I'd love to be able to suntan in Ontario, Canada. There are some important negative consequences that you need to be aware of. You have to remember, the difference between an interglacial and a glacial period is no greater than 9 degrees Fahrenheit. As temperatures increase, land ice begins to melt. The melting of land ice adds more water to the ocean. Sea ice, on the other hand, melts but does not increase the total volume of the ocean. However, as the water warms up, it takes up more space, still causing a rise. Why be concerned about a sea level rise? A ridiculous portion of the world's population lives near the coast or in an area that is susceptible to flooding. This is obviously dangerous because you're endangering billions of lives and trillions of dollars in infrastructure. Not only will the sea level rise, it'll be acidic too! Yay! The oceans take in carbon dioxide, but in the process they become acidic, because when the carbon dioxide combines with the water, it becomes carbonic acid. So, as this builds up in the ocean becomes even more acidic, and this is harmful to coral, fish, almost any type of marine life you can imagine, because swimming in a big bowl of acid is not how most life tends to thrive. In essence, the climate could quite potentially go haywire. Although many of the changes are actually caused by thermohaline circulation. This is a movement of ocean water due to temperature and salinity. It's actually responsible for the Gulf Stream. So, if the ocean's temperature increased and thermohaline circulation was stopped or slowed down or disrupted in any form, places like the United Kingdom might actually get colder because they don't have that warm water being circulated to them. Eventually they probably warm back up due to increasing global temperatures. But it's just an interesting side effect. The effects of this are pretty unpredictable, although there was an interesting study back in 1995 that found that in times when temperatures increased to about the levels we're approaching today, places like Patagonia and California were extremely susceptible to drought. And California's having a drought! Of course, there's also the plants. Plants need carbon dioxide, so with more carbon dioxide in the air, shouldn't they be better off? Well, yes, if that were the only change that were happening, but that's not the only change that's going As temperatures increase, it's true, we'll be able to farm in more northern latitudes. But the equatorial latitudes will be so hot that it might not be suitable for growing crops. And some regions might not have enough water because of the way that the temperature is changing the climate. So at first, there might be some positives and some negatives, but as the temperature continues to increase, it's more than likely that the overall impact will just be negative. Now that we've gotten through all the doom and gloom, we can actually start to focus on the important things. How do we solve the problem? Well, as I said before, humans give off a lot of carbon dioxide, but we don't take any back in. So that might be a nice place to start, if we could take some of our carbon dioxide back in. Which is really the end game, is just to try to take the carbon dioxide that we've emitted back in. Without a significant number of people recognizing the dangers of global warming, there's not going to be much funding to pull carbon dioxide out of the atmosphere. In the meantime, what can we do? Well, efficiency is huge, because people naturally want to be efficient anyway. It saves money. It's the most economically viable way. If we're more efficient, we also emit less. But what about third world countries? That's a big problem, because they're trying to industrialize, but they're using coal, which is just awful. It's an awful source of energy. In order to combat this, we need to diversify energy sources. A little bit of solar, some wind, some hydroelectric, other renewables. But then there's always the question of nuclear. And nuclear is a little bit because no one likes dealing with radioactive waste that they have to store for 10,000 years. Now the interesting thing is that there's a form of nuclear technology that doesn't use uranium as the fuel, it uses thorium, atomic element number 90, instead. And what they found is that the radioactive waste from thorium is predicted to decay in 300 years instead of 10,000 years. And because it's only 300, the problem of storage becomes much more manageable. Unfortunately, the technology for thorium reactors isn't quite fully developed. Reducing our transportation emissions will probably be the most difficult thing, because so many people are dependent on gasoline or diesel-powered vehicles. How do we get around that? Electric cars are promising, and something even more promising is using hydrogen, which of course takes energy to manufacture, but the great thing is that when you burn hydrogen, you just get water. No matter which avenue we choose to solve this problem, humans have a difficult task ahead of us. But I think we can do it, and that's why I chose this background. It's a picture of Earth, taken from Saturn by the Cassini space probe, and it reminds humans of how small we are, but we've done a lot. And as Carl Sagan once said, our posturings, our imagined self-importance, the delusion that we have some privileged position in the universe, we are challenged by this point of pale light. Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. The Earth is the only world known so far to harbor life. There is nowhere else, at least in the near future, to which our species could migrate. Visit? Yes. Settle? Not yet. Like it or not, for the moment the Earth is where we make our stand. And I think that that's beautiful. And the Earth is where we have to make our stand. I'd like to thank everyone for watching and for dealing with the low quality of the video, because my technical editing skills are really not that great. But should you have any evidence that suggests that I've said something false, or you can explain the data in a better way, which would be great, I would love for you to comment that. If it's interesting enough, I'll make a video in response, and then of course, comment the link. Again, thank you for watching.